Yes, we should. Okay. Today I'm passing out the exam in hard copies. It will also be available on Canvas if I remember to put it on. When's it due? Wednesday. Very good. At the beginning of class. Turn it in before you show up. Every minute late, you will lose some points on it. If you want to turn it on Monday or Tuesday, you can do that. But come up here and turn it in at the beginning of class on Wednesday. I will not be accepting it digitally. If you can't get it into me on Wednesday by that time, you can email me it, but I'm not great. That's just to show that you did it on time. I'm not going to grade it on the computer. Actually, you're doing it on Canvas, now that I think about it. So you have to submit it through Canvas, but you do have to upload your work for a handful of points. Okay. So you'll get this. If you need more room, write it on a separate sheet of paper and take a picture of everything. If you do not know how to upload a file onto Canvas, it's about time you learned how to do that. Okay. So you can come into office hours next week to learn that, or you can look on this thing called the internet, or you can talk to anyone in the class, or you can just figure it out. Okay. You're in college now. You're expected to be able to know how to do some things. So we're pretty much done with chapter 16. We went over titrating a weak acid with a strong base. This is very important on the exam. Let's see. Let me look at the exam real fast. This it? Okay. So for those of you who are not here to pick this up, I will publish this at the end of class. You can download the exam right here. You should not start this quiz until you have all the answers. You have one chance to submit your answers. So do the test. If you're doing it by hand, complete the test, and then you can go in and you're going to input all the scores on Canvas. Okay? Anything you get wrong, I will look at your notes and give you some partial credit accordingly, but I hope you just get it right on the first try. Okay, that way I don't have to double check it. So do not start the quiz on Canvas till you have downloaded or gotten the hard copy and completed the problems. So do the problems first. Once you've completed all the problems on the exam, don't worry, it's not multiple choice or anything like that. There's like acidic, basic, or neutral questions. But anybody, so you are allowed to um, do not start. Here's the exam. Make sure you have all the answers. Basically, I forgot to write that on here. No internet. You can use your notes. You can use my notes, and you can use anything that I have on Canvas. So if you look on Canvas, let's take a quick look at this. For exam 3, I will make this available right here. Oh, it's available. You can all leave now. You don't need to come to class. There's like 4 more people than no, just kidding. But so when you click on this, like I said, if you're not here and you're not getting the hard copy, download this thing right here. If you do it on your tablet or whatever, or your computer, you know how to take screenshots and upload those all. I want it all as a single file. For the problems, you will do, there's a problem on acidity. There's a bunch of problems on titration. And then the numbers. So it says like question 7, question 8. I don't know why it always does that. I even put in a new name for these, but it'll say like 2F, 3 ABC. Question line, upload a picture of all your notes. Do it in a single file. So if you don't know how to do that, look it up. Okay. You get 7 points for submitting these files, and this is also where you will receive partial credit. It will not tell you your score until everybody has completed when the exams due on Wednesday at 11 o'clock. I think that's when it's due. Due April 25th at 11:05. Ooh, no, I gave you 5 extra minutes. But basically, you won't know what you got till the end, so you shouldn't be able to go tell everyone. And like I said, you're not allowed to talk to anyone. If you put the same wrong answer as the person you sit by, that makes me think you cheated, and I will consider you a cheater. So make sure you guys, and really, you could make the same mistake if you studied together. So I won't automatically fail you, but just do it on your own. Aren't you happy that you're not right now 6 minutes into an exam trying to crunch out all this in 50 minutes? Is it nice to have the full 3 days? So everyone gets 3 days, but I'm giving 2 days extra. Okay, so it's due on Wednesday. Any questions on the exam? Everyone good? Okay, the other thing I wanted to show you about this was on here. So I said you can't use any internet, but you can use Canvas. If you look at this exam 3, there is like an old practice exam. Here's a practice exam. You can like look at these and they might have solutions. I don't know if they have the solutions. Exam. I don't know if that's the exam. I might look and see fall exam 3. So I think actually this one was a video going over. So this was when it was online, and this is like going over some homework problems with people. Should I post that? Let's publish that. Okay, so if you're having a hard time, you can watch some of these old videos and things like that, and you can look at stuff like that. All right? Everybody good with that? Any questions on the exam? Everyone good? Those things? Maybe not. Let me send me an email and I can try and get those available on YouTube. Yeah? So send me an email about it. And I will hopefully have those because it's a super old video. So I don't know if I have that video, but if I can find it, I will put it available. Okay. Now, so this in the notes, I go through how to solve for all these things. So once again, if you're having a hard time, the numbers are different, the volumes are different, but the steps to doing everything is the same. So I'm not going to go over all this stuff because we've gone over it in great detail over and over. But if you want to, you can look at these notes from chapter 16 to figure out that stuff. Lab this week, how was it? Your Monday? Thursday didn't finish either? Oh, okay. Well, we didn't miss much. It's basically just doing what we're doing on calculations. In lab, the data doesn't come out that great, as we always see, because the pH meters are not the greatest, but we make do with what we do. Okay. So we have today and 2 more weeks of class. We have 2 more chapters to cover. Chapter 17, I'm going to focus heavier on. It's thermodynamics and this concept of entropy. Entropy is the measure of disorder. So we should all know very well about that. We'll talk about that. We will also talk a little bit about chapter 18, probably the last week of class. I am planning on changing the last week's experiment from a wet lab to a worksheet, which will help us practice for the final exam. Would you all rather get the experience of doing another titration? All I know is when I watched my class do titrations, I saw people breaking $50 barrettes. And then I see people from the other class yesterday. I was going to complain to you all, but I forgot you had a gas leak. So I guess you shouldn't be expected to clean up your barrettes when you're, and it wasn't even a gas leak, I don't think. I think it was just a dirty sink that had fumes coming up of it, but it was still stinky, right? Those of you who were there. So I don't think I don't know what your teacher will do about that, but you didn't miss much. It was just titrating and taking the pH of it. It's not the funnest thing in the world. So let's go ahead and jump into chapter 17, and this is thermodynamics. Have we ever learned about thermodynamics before? In 115A. What was thermodynamics? What was the letter we were talking about in thermodynamics then? Anybody remember? So Q was the heat that we were looking at, and that was something that was related to, but the thermodynamic function was actually H in this case. Anyone remember what the name of delta H was? Say it for us, Jack. Enthalpy. Okay. Not to be confused with what we're going to learn about in this chapter 17, which is entropy. Make it a chemist, all the different words in the world, and they have to make it so that they're kind of close and kind of confusing. Anybody know what letter entropy is going to be? What would be the most obvious thing for it to be, Ian? Entropy. What would we have a letter for it be? We would think E, but do we already have a delta E? What does E represent already? Energy. So entropy has delta. Any guesses? S. There's no S in entropy. I don't know why. There was no H in enthalpy, but I think of enthalpy as heat, right? So enthalpy was basically the heat of a reaction and things like that we learned about in chapter 6 of 115A. In this chapter, we will continue to talk about heat and the heat tax, but then we'll talk about things being spontaneous versus non-spontaneous. Anybody know about spontaneity? Dustin, are you spontaneous in your relationships? No one? No, just kidding. So, what is spontaneity? Lucian, you seem spontaneous. Huh? Well, spontaneity is different than entropy. Entropy is the randomness, okay? Spontaneity is something else. So so a lot of people say you need to be more spontaneous. I'm not going to put any genders on it as saying which ones say that, but what are they talking about? Anybody? Nobody wants anyone to be spontaneous? Yes. Taya. Huh? I don't think that's what they mean when they say spontaneous. Like usually they're saying like a person is not spontaneous because they come home and they sit on the couch and they play video games all day. So being spontaneous in like relationships would be like, let's go for a walk or let's go to a concert. Yes, Ella. Yeah. So if you ask my wife if I was spontaneous, what do you think the answer is? Heck no. I do the same thing most of the time, and sometimes I'm like, fine, let's do something different. And then I wasn't asking you to think about what it was. I'm just saying in general for anyone, do you think I would be spontaneous? And the answer is no. I'm stuck grading and making lesson plans all the time. So when can I have some spontaneity, right? So in science, what do you think spontaneous versus non-spontaneous is? Any thoughts? Yeah, Emily. By itself. So a spontaneous reaction will happen in the forward direction without help. A non-spontaneous reaction will not happen on its own. Does that mean that we can't make something spontaneous? Can you make a non-spontaneous person spontaneous? Yes, you force them to, right? You're like, no, we're going to the whatever is going on. You know, there's all kinds of cool stuff on campus that you all could do, but we all want to just sit around and look at our phones and do that, okay? So in chemistry, if something is non-spontaneous, we actually have to add energy to it to make it happen. A spontaneous reaction will happen without the added energy. So that's just kind of like a summary of all the things that we're going to be talking about. The first law of thermodynamics, you cannot win. What does that mean? Any thoughts on that? Are we talking about the Golden State Warriors for the rest of? I'm just kidding. What are we talking about when we can't win? We're talking about the law that energy cannot be created or destroyed, so we cannot get energy out of nothing. Someone could say, what about solar panels, right? Solar panels are free energy. What happens if the sun disappeared? So the sun is emitting energy, right? If we think about any kind of like energy that we make, when you have electricity in the room, for us, it's free energy, but is it really free? We're paying as students, we're paying as taxpayers, someone's paying for it, right? And really, with energy, all of energy has a little bit of waste, okay? When you charge a battery, the amount of energy you put into charging it, you'll always get less energy back out of it than what you put into it. So that's what they mean by saying you can't win. I mean, you can win at a lot of things, right? You should win. You should make the best out of whatever you do. But the first law of thermodynamics is saying that energy cannot be created or destroyed. Back in the day, there was people who, back when America was young and people would like try and like sell things, if you watch like the circus and things like that, someone's like, "Oh, I created this machine that is a everlasting energy and you can have free energy forever. Buy into this." That is just a salesman gimmick, and you cannot create energy out of nothing. It always has to be come from something else, right? So the total energy of the universe cannot change, but we are able to transfer it from one place to another. Batteries are one way to store energy, things like that. So the first law of thermodynamics, and if you've taken physics, you've learned this. The delta E of the universe is equal to zero, saying that all the energy of the universe is a combination of the system and the surroundings. So if you think back to, chapter 6, when we talked about energy as heat, we always said that, an exothermic reaction, it's not like the energy that is created from it, some of it is lost to the environment. We use things like calorimeters to try and minimize the energy loss. But if you went back to like chemistry lab, the data was never perfect, right? Kind of like all the data we have in lab, it's always not perfect. And there's a lot of loss that we don't account for. So with the conservation of energy, we have the term exothermic, where heat is lost, where we say that heat is lost from the system and it goes into the surroundings. So burning of wood is an exothermic reaction, right? If the wood and the fire is the system, the heat gets transferred outwards to the surroundings. So if we're sitting by a fire, we're benefiting from that warmth heating us up. If we're heating up a fire to warm up our house in the middle of winter when it's cold, or on April 25th when it's freezing, right? We just had like a nice little hot spell, and now we're back to freezing cold, whatever month it is. It should be past spring, right? We should almost be getting into summer. But in general, there's two ways that energy can be lost from a system. One is in the form of heat Q, the other is in the form of work W. Do these variables kind of ring a bell? So Q is the actual heat, the delta H is the overall heat that something can have. We said that energy conservation requires that energy change in the system is equal to the heat release plus the work done. So the total energy of a system is equal to the amount of heat plus the amount of work. If you remember back, heat was delta H and work was the change in volume across a pressure. This is more thinking about like how a car works. A car burns gasoline. That exothermic reaction causes the pistons in the engine to fire up and down, and that firing of the pistons creates the turning of the wheel shaft or whatever, and that's what gives us power in a car, right? So when you have like a 8-cylinder car versus a 4-cylinder car, that 8-cylinder car has more pistons that are doing work inside those things. The bigger your piston, so if you think about like huge tractors, they probably have these huge pistons and they're generating more power when you're burning the fuel and things like that. So all of that's going to come into play. We say that energy is a state function. Anybody remember what a state function was from 115A? Not one person in here. Lucian, looked like you raised your hand. He did though. So Nate, what's a state function? So what does independent of how it's done mean? What does that mean? So basically, when we say gasoline has some amount of energy associated with it, right? So if we wanted to compare the amount of heat we can get from burning some gasoline versus burning some wood versus burning some propane, do we have anybody ever heard how there's like different sources of, anybody ever hear about the hydrogen powered cars? Anybody ever seen one of those? So I had a friend who had a car that had a big gas uh hydrogen tank in his trunk. So he basically had no trunk. And he was telling us how it was like more efficient than gasoline in the bang per buck. But we're like, well, what happens if you want to drive somewhere and you want to fill up your hydrogen tank? He's like, well, I was like, what if you want to go to Tahoe? He's like, oh, look, I have this little map that shows you where all the hydrogen stations are. He's like, you can just stop off in Chico and fill up. I'm like, do you not know that Chico is not on the way to Tahoe and there was no hydrogen station? I mean, so it was a good in theory, right? The electric car 10 years ago when it first came out was cool, right? But why was it not great? It didn't have a long battery and it also didn't have a lot of charging stations. Nowadays, there is a decent amount of charging stations, especially in California, right? So I feel like Teslas are like have a bad rap now. But if you have one in California, there's a lot of places to fill up your Tesla, right? But if you were in the middle of the country, there's a lot less places. Wouldn't it suck if you go pull up to a Tesla charging station and there's 7 cars waiting in front of you? Now you have to wait an extra 4 hours on your cross country road trip. So all of those things are going to make a difference. What a state function is it's saying that we don't care about the absolute energy something has. All we care about is how much energy it gives us at the end of the day. Okay. So it's basically like, kind of like, what is your net worth? Like maybe you have a bunch of, when they say like how much liquid money do you have? Like if you had to like leave the country on a whim, someone could be a millionaire, but they have like houses that are worth these millions. That's great versus someone who has 4 gold bars. They can take those gold bars and turn it into like money right away and stuff like that. So a state function is basically saying we don't care how the energy is made. All we care about is how much energy is given out. So that's why we always see these things as a delta E, and that might confuse us because delta always means change. Really, in all these things, we're just going to think about it as how much entropy something has is going to be delta S. How much enthalpy something has is delta H. How much energy something has is delta E. These are all a change is a weird thing to do, but that's just saying how much can we get out of that in terms of those things. So the energy tax, you can't break even. To recharge a battery with 100 kilojoules of useful energy will require more than 100 kilojoules of energy because electricity has to flow from the charger to the battery. What is one of the biggest draws to Las Vegas? Anybody in here ever go to Las Vegas? What's the draws? Okay, I want to know the clean draws, okay? I don't want to know the bad draws that you all go there for. Yeah, Robert? Well, the gambling, yeah, but let's not talk about most of these people are not old enough. So what else? If you're a kid in Vegas, what's cool, Lucian? The lights, right? Isn't Vegas super Yes, Ricardo. Cheap stuff. That's cool too, right? Yeah, Nana. Huh? That place is so expensive. So you guys are talking about two exact opposite things, right? You got to pay like 50. Eh. So the cool thing about Vegas is the lights, right? Like a lot of people go there. And do we consider the lights in Vegas extremely excessive? Do we say Vegas in general is an excessive place? I mean, once you start going there for like bachelor parties and bachelorette parties and things like that, you're like, oh, that was a waste of money and a waste of energy. But you know why they're able to waste all that electricity? Because they're super close to a place that generates huge amounts of electricity. Anybody know what that is? The Hoover Dam, right? So a lot of that energy gets taken over to like the Los Angeles area. But how are they going to transport that electricity from the Hoover Dam to Los Angeles? How do we think, Ray? What do you mean you put something in the middle? How is electricity transferred, honey? With wires. Very good. Okay. So if something is running through a wire, there's a little bit of static, there's a little bit of heat. If that electricity has to travel 500 miles, you might lose 10 to 20% of that electricity just in transport. If it only has to go 20 miles to Vegas, their rationalization is, well, we're not wasting all this electricity transporting it, therefore we can use it. And that's not a good thing to think of, but that's why they are so frivolous with their lights and things like that. Okay. So we call that like traveling of the electricity an energy tax. When you charge your cell phone and things like that, you lose electricity. When you do that, you should theoretically only charge your cell phone till it's full. But when we leave it on all night, is that wasting electricity? Yes, it is. Realistically, you should unplug your charger. Who leaves their charger just plugged into the wall? So whenever you want to use it, you can just plug it right in. Well, you're wasting electricity. If you want the world to stop being carbon bad, unplug it. But I do the same thing. So, but I do turn off my lights anytime I leave. I do things like that. Okay. So if you can take little steps to like reduce your electricity consumption, it goes a long way. If you do it and your roommates are like, why are you turning off the TV? We're going to be back in 2 hours. I want it to be on right when I walk in so that I don't have to go and push that button. You can be like, well, that 2 hours is wasted. Let's just turn it off. And then when we come back in, we can push the button, right? So little things like that would go a long way. And when you start to do things, maybe other people start to do things, maybe your family members start to follow in suit. It's a chain reaction. We can't start like conserving until you individually does it. Does it matter in the whole scheme of the 9 billion people on Earth? Is that an overestimation? We're not counting all the underground people and stuff like that. But in general, it has to start with you. So start doing little things to conserve energy because you're always losing when you do it. So let's take a look. If we heat with natural gas, you heat with natural gas and it directly heats your house. When we heat with electricity, at some chemical factory, at some power plant, they burn fuel. That fuel gets converted into energy. There's a little heat tax. That energy makes steam to power a turbine. There's a little heat tax. That electricity that's generated from the turbine travels through a wire. There's a heat tax. That wire goes to charging our flashlight. There's a heat tax. Then when we shine that light, there's another heat tax. That's not a great thing. We should have made this into like a heater. It'd be more realistic if this was a heater that heated us up. And then for the same thing, this has one heat tax because you burn the fuel and it heats up your house versus using electricity. Does anybody know that they're trying to get rid of natural gas heating and things like that? They're trying to get rid of gas stations. Like, because why is the reason that if we look at this slide here, it tells us that burning fuel has less heat tax. So why are they trying to get rid of natural gas and things like that? Anybody have a thought? Huh? We would think it was about the money, but it's actually, what is the big byproduct here? Carbon dioxide emissions. Carbon dioxide emissions are terrible on this earth right now. This also has CO2 emissions if we're actually burning fuel. A lot of power plants are actually starting to, there's a lot of people with solar, right? That's why they had like solar rebates and things. When people start doing solar, it almost feels like free energy, right? Because we're just taking the sun and that sun's just like kind of creating energy for us, right? But there are other stipulations. But the reason why that they're trying to get rid of gas is because it directly makes CO2. If we have alternate ways of creating energy, whether it be solar, wind power, hydroelectric. There's the future of energy. Anybody know what it is? The cleanest energy? Nuclear. Why is everyone so hesitant to do nuclear? Huh? What do you all know about nuclear energy? What do you hear about nuclear energy? Well, the bad stuff, right? The meltdowns, places like Chernobyl, places like there was one in Massachusetts somewhere, in Japan when there was that tsunami. Remember there was that on March 11th, 2011. Oh, is that weird that I know the date of that tsunami? When my daughter was born. Um, that is there was a water like a there was like a tsunami warning and things like that, but the power plant had a nuclear meltdown, and we think of all the bad things, but when it works good, it works amazing, and it has almost no carbon dioxide emissions. The other bad thing about nuclear power plants is it takes a lot of money to get them started. Once you get it started, it gets cheaper and cheaper, as with anything, right? If you build a house to live in it for 1 week, nobody really does that, right? But if you build a house to live in it for a lifetime, it seems worth the investment, right? So you have to think about things like that. I would say that this is just showing you that the more times you have to transfer energy, right? So if you charge your battery and then the battery charges your phone, that's less efficient than charging your phone directly. But sometimes we need that battery, right? If we're going to go out camping for a few days or we're going to be on a long road trip where we don't have something, we want to have a battery. So we still do that. But in general, the less steps you have to take, the more efficient that charging is. Let's do a quick conceptual exercise. Advocates of a vegetarian diet argue that the amount of cropland required for one person to maintain a meat-based diet is about 6 to 10 times greater than the amount required for the same person to maintain a vegetarian diet. Apply the concept of nature's heat tax to explain this assertion. So, anybody in here agree with this? Anybody ever hear people explain to you why they're vegetarian or vegan and how they're saving the earth? So, based on this, how does that work? Any thoughts? Yeah? So the steps are going to be very different, right? A person who just straight eats vegetables and fruits, they're getting their energy, and there will be a little bit of that energy not being efficient to power your body. But if you eat a cow that ate the grain and it had to process that food, and the land is not even in this argument, but that's also a thing. Since the cow has to break down and resynthesize biological molecules. So, because of that, I am not going to eat meat for the next 20 minutes of this class. Okay. To minimize this heat tax. Can you cut back on your meat? Yes. Nowadays, is meat pretty expensive? It's only going to get more expensive. Actually, I don't follow. It looks like there's some cutbacks in everything going up, but who knows? Regardless, if you are a vegetarian, you can say you're doing it for the energy and things like that. You can say whatever you want, but at the end of the day, producing animals to eat is going to be using more energy than if you just were to eat the vegetables yourself. But why does not everyone go vegetarian? Any thoughts? Riley? Yes, because meat tastes good to some people. So, thermodynamics is going to help us predict whether a process will occur under a given set of conditions. Processes that will occur are called spontaneous. A process that is non-spontaneous will require energy for that to happen. Somebody give me an example of a spontaneous situation. What's something that's spontaneous? If I say that I'm giving a quiz spontaneously, more people will come to class. That's not a spontaneous situation.
Spontaneous would be like you're just out doing your things and then you're suddenly like, hey, I'm gonna go for a hike and like
Well, we're talking about chemistry spontaneous. So think I know. What is a spontaneous situation? What about if I take a ball and I put it in the middle of a hill? Will that ball spontaneously roll down the hill? Most likely, right? So a situation could be if you put a ball at the top of a hill, it's spontaneously going to roll down. Is a ball ever going to spontaneously roll up a hill? Huh? No? Anybody ever been to the mystery spot in Santa Cruz? Does the balls roll uphill? It looks like it though, right? So is that breaking the law of thermodynamics? What about Gravity Hill? Anybody ever been to Gravity Hill? It's like a couple miles away. Anybody ever roll their car backwards spontaneously up the hill? Try it out. I'm sure the people who live there don't like it, but I went there one time. I was like, this is like some people who live in the country. I don't want to get shot at, but there is a place, and all that's doing is you are rolling downhill, but it makes you feel like you're going uphill. Okay, so balls will always roll downhill, and why is that, Meredith? Why do balls always spontaneously roll down hills? Because of gravity. For that same reason, if I take my cell phone and I let go of it right here, what's going to happen, Alondra? I'm not going to drop it, so I don't know, but it would fall, right? So spontaneous processes would be like a book falling when you drop it and a ball rolling down a hill. Now, is it non-spontaneous for my phone to get up to this height right here? Yes, but can it be done? Did it just happen? It happened, right? How did it happen, Ricardo? So what did I add to it? What is that? That's work or energy, right? I added energy to make a non-spontaneous process happen, okay? So not just the fact that something's spontaneous or non-spontaneous does not mean it will not happen. It just means you have to put energy in. And we take that to our advantage, right? So spontaneity is determined by comparing the chemical potential energy of the system before the reaction with the free energy of the system after the reaction. So we're going to learn about chemical potential energy in this chapter, and that's going to be called delta G, and that's basically going to tell us about spontaneity, if a reaction is spontaneous or non-spontaneous. Okay. Um, if the system after a reaction has less potential energy than before the reaction is thermodynamically favorable. So my cell phone up here, does it have a lot of potential energy? Does it have more potential energy than when the phone's over here? Yes. More potential energy up here, less potential energy down here. So at the end, it's going to go to the thing of less potential energy because it wants to go down, right? So that's one way to think of it. Spontaneity has no. So we learned about kinetics at the beginning of this class, right? Chapter 13. I finally graded my formal reports for my class only about 2 months later. So no one even remembers anything about it. But if something's spontaneous, that doesn't mean it's going to happen fast or it doesn't mean it's going to happen slow. That is kinetics. That's a whole different thing. It just tells us if it wants to happen. Diamonds spontaneously convert to graphite. So when I bought my wife a diamond ring for our engagement, it was tiny. It was like the smallest diamond you could get, but we're in grad school, okay? So if you need a reason why you want to propose and you can't afford an expensive ring, just be like, well, I learned in chemistry that diamonds spontaneously convert to graphite, and I don't want you to be upset when that diamond turns into graphite. Well, even though it's spontaneous, it is unbelievably slow. It has a huge activation energy, and it's not ever going to happen unless you do some things to force it to happen. Okay, so those are some things to think about. And that argument didn't work with my wife, even though she was a chemist, and it should have worked, right? So I just had to be spontaneous. I'm just kidding. You just had to do things. So this car here, if I go and leave it outside for 20 years, is it spontaneously going to turn into that car on the right? Yes. Does anyone ever put this car outside and 20 years later come back and the car look like that? Unfortunately, no, right? But can somebody take this car and make it look that way? Merve, could they do it? And how would they do that? I mean, you can do it, but what do you have to put in? Time and money or energy, right? So you'd have to put in energy to convert it. But do you have to put in any energy to get that shiny new car to start looking like that rusty old one. So the chemical speaking wise, the nice shiny car would be spontaneously converted into an old rusty one, and the rust is happening. I mean, you could keep it from that happening. You could put a cover on it. You could leave it in a garage. You could polish it regularly and things like that, right? But in general, you're putting in energy to keep that thing from happening. So that's a intro to spontaneity. Um, a spontaneous process is irreversible because there's a net release of energy when it proceeds in one direction. That means that if a process is spontaneous in one direction, it is non-spontaneous in the other. Reactions that are reversible means that it is not spontaneous or non-spontaneous. That means that the reaction can happen in both ways. The direction of spontaneity can be determined by comparing the potential energy of the system at the start and the end. So when we pull this thing up, we're putting energy in. That's the non-spontaneous direction. Once we let go of it, it's going to drop because of gravity. A lot of spontaneity is going to be determined on gravity. Okay? In reactions, we've seen these things, right? What was this gap to this gap called? Anybody remember? What's it called? Sydney? It was a question on the exam. You don't remember, Dustin? Zeus? What's it called? Activation energy. We should have known that, right? We did a formal lab report on that. We also, so that's activation energy. So did everybody see that I inputted corrections for the exam? I also put in zeros for, maybe I didn't do that for this class, for any missed quizzes. I will go do that. Usually people are like, oh, I missed this quiz, but it didn't affect my grade. I haven't put in a zero yet. I'll put in zeros to like wake everyone up and let you know you're not doing well. You should know if you missed the quiz, right? If you didn't, you're not keeping up with the class. Now, I only had out of 107 people, less than 30 people who did corrections. Okay. Some people you have an A, fine, you don't need corrections. If I said corrections were extra credit, which they are, right? If you don't do corrections, did you lose any points? So if you do corrections, are they extra credit? If I start calling corrections extra credit, would people go out of their way to do them? Because when I give 2 points extra credit, someone will drive to like another school and go help like a bunch of little kids in chemistry for 2 points extra credit. But if I say correct your exam and learn what you did wrong, they're like, that's only 15 points. He never said extra credit, so I won't do that. So in the future, we don't have any more chances to do corrections. But in the future, when a teacher gives you the option to get extra points to do corrections, what do you think you should do? You should do them, right? Because A, it makes you better at that subject because you're learning what you did wrong. And B, you're getting free points, extra points that do not hurt you. So it was extra credit. So I don't understand the 70 of you. Well, there's like probably 30 of you who had a score that they didn't think they needed extra credit for. But the other 50, you're just going to like be like, yeah, I didn't do good. I don't even want to look at this. Learn to do the things that give you the free points. Okay. So going back to this slide, thermodynamics versus kinetics. Kinetics states the speed of a reaction, okay? The thermodynamics tells us energetically, does that reaction want to happen, okay? So we're going to look a lot at these things over the next week. If I was in this class and I wanted to be successful, I would look at the slides beforehand. You probably will not understand much of them, but you'll at least have seen them one time. And then when I go over them, you're not seeing it for the first time. Okay. That's why when you like are on a sport, if you're running a cross country meet, you go and check out the course beforehand, right? So that even though you're not going to memorize that course, you might just be like, oh, this looks like a crazy part. I should know to like be ready for an uphill at the very end or something like that. If you look at the slides beforehand, it might help you. I guarantee you it won't hurt you. Okay. It's going to be intense for these last 2 weeks, and it's not going to be intense because we're going to be rushing. It's just a lot of completely new stuff that we haven't learned about or we have learned about and you just don't remember it. I mean, I don't really expect you to remember stuff from 115A, seeing as when I ask you about something that I talked about last week, you usually don't remember. And when I talk about something at 11:05 today, you're like, I don't remember that. I didn't put that in my thinking bank yet. So let's learn that. So we're going to look at reactants and products. When the products have higher energy than the reactants, for that reaction to proceed, that's an endothermic reaction. That reaction must take energy. It must absorb energy for that to happen, right? So we're going to see that most endothermic reactions are non-spontaneous, but that's not always going to be the case. We're going to see that's not true, right? So can anybody think of a endothermic process that is spontaneous? So something that happens spontaneously, but is endothermic. Can somebody just think of an endothermic thing that happens? What is something that absorbs heat? An ice pack. So when you break that ice pack, it absorbs heat, right? Let's think about ice in general. Is the melting of ice an endothermic reaction or an endothermic process? Does it absorb heat from your hand to melt? So that seems like you have to put energy in, right? But if I took a piece of ice out of here and I put it on the floor right there, is it gonna spontaneously melt into liquid water? Yes, it will, right? Will it always spontaneously melt into liquid water? What if it is in Arctic Alaska in the middle of winter? If I take a piece of ice out, is it going to spontaneously melt? No. So we're going to see that some processes are spontaneous above a certain temperature and non-spontaneous the other way, or vice versa. Some processes are always spontaneous. Some processes are never spontaneous, okay? So we're going to look at all of those things next week coming up. So, but I just want to show you some examples of how those things happen. Usually you have to put energy in. So there's still energy being put into the ice when it's melting right here, right? Why is the ice melting right now in the middle of the day? Any thoughts? The heat from the room is going into it, right? When it's super cold, there isn't that extra heat to go into the room to cause that to happen. So those are some things we're going to think about. Look at this, a diamond. That pretty much looks like the diamond that I got my wife, except minimize it by as much as they can make it smaller. And it will spontaneously go into graphite. Okay? So use this. I promise you, if you have to get a ring for someone or diamond earrings, get the little ones and be like, you'd be so sad if those earrings turned into this. So I'm just saving you future. But actually, it happens at an extremely more rate. So graphite is more stable than diamond. So the conversion of diamond into graphite is spontaneous. But don't worry, it's so slow, your ring won't turn into pencil lead in your lifetime or through many of your generations. So unless you're thinking long term, 7 generations from now, which is the way we should be thinking, but even in 7 generations, that diamond's not going to convert to graphite. Okay. So a spontaneous process occurs because they release energy from the system. We just said an endothermic process could be spontaneous. Am I contradicting myself? Is it Friday and I'm just like end of the week and I don't even know what I'm talking about? Or you think there's probably, right? It is Friday. And it's basically the last Friday of this class, besides next Friday and the Friday after. But when we can say that, that's not that many, right? So we're at the home stretch. Let's finish off strong. And remember, we have a take-home exam. That should be a booster for everyone to boost up your score, right? Take your time, think about it. So it's 11:50 now, so that's the end of class. You can all, I'm not going to pass these out. You can come pick it up. It's a super long exam. It's one sheet of paper front and back, okay? We'll continue on Monday. Have a great weekend. Aloha. You're welcome.